Okay, the next one is 4.3. So the concept of heat, work, and internal energy. Heat, the symbol, when you represent heat, we use a capital letter for Q, and the unit of heat is joule, and it's a spontaneous flow of energy into or out of the system caused by difference in temperature between the system. We can say system A or system B and its surrounding, or between two objects. You can consider between two objects whose temperature are different. Another aspect of this definition of heat is that a body never contains heat. Rather, heat can be identified only uh, as it crosses the boundary. So that's heat is a transient phenomena. So heat is it can be represented transit in energy. Okay, now let's proceed to the next one, which is a work. In addition to heat, work, and the unit is joule. It's non-spontaneous energy transfer into or out of a system due to force acting through a displacement. For example, you can consider a piston. So when you push a piston downward, so there is a displacement in the position of that piston, or there is a decrease in the volume. So due to that displacement of applying of a force, so we have done a work on the system. And sometimes there is a work done by the system. So when the piston moves upward, so work takes many forms: moving a piston, or steering, or running an electrical current through a resistance. This all is forms of work. So work is non-spontaneous transfer of energy. Heat and work are two possible ways. This heat and work are two possible ways of transferring energy from one system to another system. So in transfer in the form of heat or in the form of work. That is the representation of heat and work. So whenever we define first law of thermodynamics, we consider heat and work, and as well as the internal energy. So the energy transfer in these two different forms in order to change the internal energy of the system. Just considering the conservation of energy. Okay, the next slide is the concept of heat. Heat is a microscopic forms of energy transfer involving large number of particles. The exchange of energy occurs due to the individual interaction of the particles. So when the particles interact, they exchange energy with each other. One loses energy, the other will gain energy. So no macroscopic displacement occurs when heat flows. So in case of this heat flows, we consider the microscopic, not macroscopic, the microscopic. So no macroscopic force is exerted by one object on the other object. So a system cannot possess heat or work. These two are energies that flow into or out of the system. Heat transfer obeys the laws of conservation of energy. If no heat is lost to the surrounding, or we can say that in general during the loss and gain. So if one system loses energy, the other system will gain energy. So if there is if the two systems are can be possibly exchange energy with each other and they are isolated from the external, then in this case if one is at higher temperature, the other is at lower temperature, so there is a possibility that the two systems exchange energy, considering the boundary can allow heat transfer from one to the other. So in this case we can say that the Q, the heat lost by hot object, is equal to Q gained by cooler object. Cooler is at moderate temperature and hot is at large temperature. Now let's to the next one. The other one that we need to consider here is internal energy. The symbol for internal energy is defined as the energy associated with random disordered motion of the microscopic components of atoms and molecules. Whenever we say a bulk kinetic energy, it considers the motion of this bulk matter, like we can consider a certain car starts from a certain velocity and considering as initial velocity and goes to somewhere and acquire a final velocity. In that case, it's possible to find the change in kinetic energy, where half m v final square minus half m v in kinetic energy. So the kinetic energy of that is final minus the initial square, so due to the motion. This is for bulk material. So in case of this one, in case of the molecules, internal energy includes the kinetic energy of translation of those molecules. It may be in the x, y, and z. In this case, we say that half mvx square plus half mvy square plus half mvz square will be the translational kinetic energy of those particles. Whereas some molecules, like the atomic molecules, there is a consideration of rotational. The molecules will rotate, so the rotational energy will be considered. And those molecules, sometimes they have a vibration of those molecules. So the vibrational energy of the molecule will be considered. Potential energy within the molecules also, and the potential energy between the molecules will consider. All these contribute to the internal energy of the system. Therefore, now it is useful to relate internal energy to the temperature of an object, but this relationship is limited to some extent. Whenever say limited, we have this important point. Internal energy changes can also occur in the absence of temperature. Remember that internal energy change can also occur in the absence, not the present. In the absence of temperature change, it is possible to acquire internal energy. Okay, the next slide is all about specific heat. The quantity of Q required to change the temperature of a body of mass m by changing T is proportional to both mass and change in temperature. So we know that Q is directly proportional to mass multiplied by this change in T. Then the constant of this proportionality is represented by C. Therefore, Q is equal to mc change in T, where C is the specific heat capacity of that material or that gas, fluid, whatever. If it is water, the specific heat capacity of the water will be considered. So mathematically, the proportionality constant called specific heat capacity, or in short, specific heat of the substance, defined as the amount of heat required to raise the temperature of a unit mass of any substance through a unit degree. It is SI unit. The SI unit of representation of this one can be joule, because C is equal to Q over M change in T. Q is measured in joule and mass is in kilogram. Change in T is in Kelvin. So joule, kilogram, Kelvin, or joule, kilogram, degree Celsius can be the unit of specific heat capacity. Okay, so the amount of heat required to change the temperature of n moles of a substance, usually for a gas, is given by, in this case, Q is equal to n multiplied by C multiplied by change in T. So n represents the number of moles, C is the heat capacity. So C, the capital C, is the heat capacity, not specific heat capacity. In this case, it's the heat capacity defined as, this heat capacity can be defined as the amount of heat energy required to raise the temperature of substance by 1 degree Celsius. To raise the temperature of substance by 1 degree Celsius. So next to this one, we have to see latent heat. So latent heat is the heat required per unit mass of substance to produce the phase change. Whenever we say latent heat is required not to change the temperature, but to change the phase change. The phase change means to change from solid to liquid, or from liquid to gas. So to change this from solid to liquid or liquid to gas, the energy that's required is latent heat. So latent heat, QL, is required to change the phase of M mass of a body at constant temperature, and it can be calculated as QL is equal to plus or minus M times L. That is latent heat. If it is latent heat of fusion, so we have to use F. If it is latent heat of vaporization, we have to use F. Okay. Next to this one, we know that L is a specific latent heat required to change the phase of 1 kilogram of a substance at constant temperature. So next to this one, there is an important table. This table contains melting point, latent heat of fusion, boiling point, and latent heat of vaporization. For example, for helium, the melting point is minus 269.65 degrees Celsius. Latent heat of fusion is 5.23 times 10 raised to 3. 5.23 times 10 raised to 3 joule per kilogram, and boiling point is minus 268.93 degrees Celsius, and vaporization 2.09 10 raised to 4 joule per kilogram. That is for helium. But for water, the melting point is 0, latent heat of fusion 3.33 times 10 raised to 5, boiling is 100, and vaporization is 2.26 times 10 raised to 6 joule per kilogram. So We have also for sulfur, lead, aluminum, silver, gold, copper, and so on. We have these points: melting, boiling, latent heat of fusion, latent heat of vaporization. So in question, we have to use these constants to solve different question. Okay, so there are the types of latent heat. There are two common types of latent heat transfer. The first one is latent heat of fusion. The second one is latent heat of vaporization. This latent heat of fusion is heat absorbed or released when a matter melts, changes phase from solid to liquid form at a constant temperature. For example, to change 1 kilogram of ice to water at 0 degrees Celsius, we need this mass amount of kilojoule, that is 330. Okay, latent heat of fusion. The two types of latent heat transfer between an object and its environment. Latent heat of fusion, the heat absorbed by released when a matter melts, change from solid to liquid form at constant temperature. For example, 3.7 kilojoule heat is required to change 1 kilogram of ice to water at 0 degrees Celsius. So for water, latent heat of fusion is 333.7 kilojoule per kilogram. Whereas latent heat of vaporization, which is L sub V, is heat absorbed or released when a matter vaporizes, change from liquid phase to gas phase. It requires the lead to change 1 kilogram of water steam 100 degrees Celsius. This much, which is 2,256 kilojoules of heat is required. And so latent heat of fusion is equal to 2,256 kilojoule per kg will be the value of latent heat of vaporization. So from this you can understand that this amount of heat Q, which requires only to change the phase, that means from solid to liquid or from liquid to gas, but the temperature is constant whenever you calculate this value. Okay, so having this in mind, there is an important table, and this important table you get a specific heat for different elemental solids or other solids or liquids. For example, for aluminum you have 900 joule per kg per degree Celsius, or it can be 0.15 calorie per gram degree Celsius. So you can take one of them based on the type of different equation. And for other, like we have to take water at 50 degrees Celsius, we can have a C value which is 4,186, and in terms of calorie gram degree Celsius, it is equal to 1.00. In steam form it is around 2000. Okay, so based on this, the water during the ice form and during water form or steam form, they do have different specific heat. So even if it's water, so at different phase they have different values. See, so whenever you solve question, you have to use different values of the specific heat capacity. And there is an example. So how much, consider this example, how much heat energy is required to change this much. The mass is already given, 40 gram of ice cube from a solid at minus 10 degrees Celsius to a steam form which is 110 degrees Celsius. So in this case, we need to have 5 Q. So we can say that Q total is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. So the Q1 is the energy that is needed to change from minus 10 degrees Celsius to 0 degrees Celsius. So that Q1 is presented by the Q of ice, which is mass of the ice. Mass is already given here. And C, specific heat capacity in ice case, so change in temperature. Change in temperature is from minus 10 degrees Celsius to 0 degrees Celsius. So the mass, when you change this 40 gram into kilogram, it becomes 0.04 kilogram. The specific heat capacity, when we consider the ice, it will be 0.49 kilocalorie per kilogram degree Celsius. And this is the change in temperature. From minus 10 to 0, the change is 10, it's known. Then finally we'll get 0.196 kilocalorie. This is only the first one, which is Q1. Q2 is just to the energy needed in this case is the energy to for phase change from solid to liquid. So in this case we have to use latent heat of fusion. So we have a mass of the ice which is 0.04 kg, and the latent heat of fusion is 80 kilocalorie per kg. So this will become Q2 will be 3.2 kilocalorie. The other one, Q3, is used to change from 0 degrees Celsius to 100 degrees Celsius, which is we can represent by Q of water, which is mass of water C, the specific heat capacity of water times change in T. Change in T is 100 because it is from 0 to 100, which is equal to 100. So the specific heat of water is 1. Here it is 0.49 during the ice, but here it is 1 kilocalorie per kg per degree Celsius. So when you multiply these together, finally you get 4 kilocalorie. This is Q3. Q4 is only needed to change from a liquid phase to gas phase. So it is latent heat of vaporization, where the mass is already known. Latent heat of vaporization for water is 540 kilocalorie per kg. So multiply this one, you'll get 21.6 kilocalorie. This is Q4. The last Q, which is Q5, is to change from 100 to 100 degree Celsius in steam form. So which is the mass is known, and this in steam form is 0.48. Now you can compare. Here it is 0.48, here it is 1, and it is water. For ice it is 0.49. For steam it is 0.48 kilocalorie per kg degree Celsius. So the change is from 100 to 100 degrees Celsius, which is 10. So multiply this one, you get 0.19 2 kilocalorie. Then finally, the heat required to change this ice, 40 grams of ice cube, from solid to steam of 110 degrees Celsius, solid of minus 10 degrees Celsius to 100, is the sum of all these Q values. The sum of this, the first one 0.196, 3.24, 21.6, 0.196, and finally you get this result. This will be the final result. So whenever you solve such type of question, remember that if there is a phase change, here in this case we have two phase changes. One is from solid to liquid, and the other is from liquid to gas. So sometimes in different question you may have only one phase change, from liquid, maybe from liquid to gas. So in that case you don't need to forget to calculate the Q value by considering latent heat of vaporization. Okay. So the next one is an example which is related to that one, the previous one, and the other one is regarding heat transfer. 4.5 is heat transfer mechanism. Heat may be transferred from one place to another in three ways. The first one is conduction, convection, and radiation. These are the most known form of or mechanism for heat transfer. So there is also a consideration in direct burning. Now let's see each one by one. So in this diagram you'll get three of them, including the direct burning. The first one is conduction. So the heat, there is the source of heat is here, the burning of certain wood maybe or charcoal, so you get heat. So the heat can be transferred through this conductor. So this is a conduction. The other one is convection. Convection actually happens in liquid and gases, not in solid, because the particles do not move. In this case the particle can move, so the cold particle will go downward, the hotter one will go upward. So this is a convection. The other one is radiation. The heat that you get from the sun is considered to be radiation. Okay, for more elaboration, conduction occurs when heat energy travels through a body, passing from particle to particle as they vibrate against each other, one with the other. So a good conductor must have particles which are very close enough in order to conduct it together, to collide with sufficient force for energy to be transferred. In this case we get a conduction. Metals are all good conductors of heat, especially these metals, copper, aluminum, and silver, considered to be the best conductor of heat because they have free electrons, which are easily able to transfer heat energy. This is the best example that we have. So burning no, this is considered to be a certain metal type. So the first heat transfers through this one because of this free electrons, because of the close enough of this particle. So the heat from here travel through these conductors. Then finally, it will affect the hand. So that's why we get here from this type of candle. And the other one is convection. When you elaborate more, convection is a transfer of heat by a movement of heated particles themselves. This can only take place in liquids and gas, because solids, the particles are not able to move from their fixed position. That's the reason which we get only convection in these two. So when a solid of a gas is heated, it expands and becomes less dense. So this is a best example that we have. So we apply heat to this liquid, and so this water. So in this direction, as you saw, this is counterclockwise motion. The counterclockwise to ensure warmer water or warmer water particles goes upward, and this one, which is clockwise direction, the cooler one, is going down. That is an example of convection. So the particles goes down and up. With this, there is exchange of energy. So radiation is the way we receive heat energy from the sun. It does not require a medium for its transmission. That is, it can travel through empty space. That's radiation, and is in the form of electromagnetic energy waves, which travel in the way as light or radio waves. So when these energy waves fall on a body, the energy may be the energy that comes from the sun or from any other source, which is in the form of electromagnetic radiation. So that may be absorbed by the material, or it may be transmitted by the material, or it may be reflected by this material. Let's see this schematic diagram. There is a schematic diagram. So there is incident radiation, electromagnetic wave comes in this direction, and some of them may be reflected by this material, some of them may be absorbed by the material, and the other may be transmitted through this material. Okay, direct burning. And some agencies use the term direct burning to describe how physical contact of flame with other available fuel spread the fire. By this form of direct fire spread, the heat of fire will transfer across any area among this fire area where there is a line of fuel for this fire to follow. So some example of direct burning are fire spreading along a piece of wood, the fire spreading along this piece of wood and setting fire to other pieces of wood in contact with. So if you have another wood, and if you place here, there is a transfer of energy from one to the other, so it follows the line of fuel. Okay, what an extinguishing agent? When a sand and water are exposed to same amount of heat energy, same amount of, let's say, 1000 kilojoule or blah blah, or 100 kilojoule, so whatever. So when you expose these two, so you will get a difference in change in temperature. If you consider 1 kg for sand and 1 kg for water, you can consider 1 kg for sand and 1 kg for water. Then after we need to deliver the same amount of heat energy, and finally you get a difference in their temperature. This is due to the change in the specific heat capacity or the difference between the specific heat capacity of sand with that of the water. So you will have observed that sand gets much hotter than water. This is because water has much higher specific heat than sand. So due to if you increase or if you have a different material with a large amount of specific heat, so the other one which have a lower amount of specific heat will have a larger change in temperature, but the one which have higher specific heat capacity will acquire a small change in temperature. This means that For each degree temperature rise, it will absorb a greater amount of heat than sand. So the specific heat of a substance measures the amount of heat absorbed by 1 kilogram of substance when the temperature is raised by 1 degree Celsius. So in order to raise this much, or in order to raise the temperature of that substance, for example water, by 1 degree Celsius, then we can see how much energy is required. That can be explained by a specific heat capacity. Okay, there is an example. It says that if the same amount of heat is supplied to sand and water of the same mass, which one would have larger change in temperature? That is the first question. The second question is, the initial temperature of a 0.1 kg of sand is 25 degrees Celsius. If 840 joule of heat is transferred to it, what is the final temperature of the sand? That is the second question. Then repeat the calculation, the above one, with the same mass of water. The same mass of water means, for example, for sand we already took 0.1 kg, so we have to take 0.1 kg for water also. Then give specific heat capacity of sand is 840 joule per kg in degree Celsius, and specific heat capacity of water is 4200 joule per kg per degree Celsius. So whenever you solve this question, you have to say that 840 joule is equal to mass of the sand 0.1 kg multiplied by specific heat capacity of the sand, which is 840, multiplied by the change in temperature. Here is the formula. Look, 840 Q is equal to MC and change in T for a sand. So the mass is known, which is 0.1 kg, multiplied by 840 is, this is the specific heat capacity of the sand, multiplied by the change in temperature. So this is the initial temperature, which is 25 degrees Celsius. Now we are going to look the unknown values, which is T2. So T2, using this calculation, T2 will become 35 degrees Celsius. This is only for sand. Now let's apply for water also. So for water, okay, this is 840, which is equal to, the mass is the same, but there is a difference in specific heat capacity, multiplied by T2 minus 25 again. Finally, T2 becomes 27. As you can see here, there is a difference between these two temperatures. This one changed from 25 to 35, 25 to 35. The change is around 10 degrees Celsius, and this change from 25 to 27, the change is 2 degrees Celsius. So due to the change in specific heat capacity, so we will have a change in temperature. So the sand will be in the sun will get much change in temperature, but in that of water will get a small change. So this is the sand and the same amount of water. So finally, as a conclusion, we can say the final temperature of the sand is 35 degrees Celsius and the final temperature of water is 27 degrees Celsius. We can see that the change in temperature of water is much smaller than that of sand, because water has much higher specific heat capacity. So the one which have a higher specific capacity will acquire a small change in their temperature. That is the conclusion we have. Okay, so the last subtopic that we have here is the first law of thermodynamics. So the first law of thermodynamics states that the change in internal energy of the system is equal to the sum of heat flow into the system and the work done on the system. In equation form, first law can be written as, this is the first law. This represents the internal energy and its heat supplied to the system and plus the work done or by the system or on the system. Okay, so having this in mind, the internal energy, which is change in U, is the change in internal energy of the system, and this one, which is the work done, and can be calculated as P change in V for a constant pressure, is the work done on the system or by the system. So P and change in V are the pressure and change in volume of the system. So in the process, we can get that isolated system is a system which does not exchange heat with its surrounding. It's already isolated. There is no exchange of particle, and there is no exchange of heat with the surrounding or with the other system. So no work is done on the external environment. So in this case, Q is equal to 0. Work is equal to, so the first law, we conclude that change in U is equal to change in the internal energy is 0, which means that the internal energy is constant. Here the change, only the change in internal, no change in the internal energy. This means, it doesn't mean that the internal energy is 0. This is only indicates that the change in internal energy is equal to 0, but this value is equal to constant. So the internal energy of isolated system is constant. Okay, now the next one is regarding thermodynamic process. So the first one is, there is a cyclic process, and there are Carnot cycle with engines operating in cycles in which the system, for example, a gas, periodically returns to its initial state. In the system returns to initial state, the change in internal energy in one complete cycle is 0, because starts from a certain state and goes to the other state and back to the original state. Due to this, the change in internal energy in a cyclic process will be equal to 0. That is, for example, it can be explained by using this diagram. Due to this, the work and Q will be equal, so the heat supplied to the system will be used to change the work or to do a work. Okay, now this is the best example. We have volume versus or pressure versus volume graph. So this is the initial state. It goes like this. So this is a path, thermodynamic process path. So the initial state, and F represents the final state. So it goes like this first, then I return back in this direction. So due to this, the system returns back to the initial state. So this is considered to be cyclic process, and the change in internal energy in this process will be equal to 0. So from this you can understand that this Q value will be equal to the work done. Okay, the other one is that we need to consider the isochoric process. In contrast, volume process, the volume of the system stays constant. So the isochoric process, it is one of the thermodynamic process at constant volume. So consequently, here we have M is equal to 0, because if the pressure multiplied by change in V is 0, so we get 0. So the first row we conclude like this. The internal energy, the change in internal energy, remember this is the change in internal energy, is equal to Q. So if you supply heat to the system, that only used to change the internal energy, not to do a work. Okay, so all the heat entering the system goes into increasing the internal energy. This implies that this is process in isochoric process. So the whole heat entering the system, the whole heat supplied in Q form, is used to increase the internal energy of the system. Okay, the other one, this one can be explained using volume pressure versus volume graph. We have this path, thermodynamic path. This path is at constant temperature path. This is another constant temperature path. From this you can understand that this temperature, this path is at higher temperature, this is at lower temperature, or we can say that T2 is greater than T1. But when you see upward, when it goes from here to here, the volume is considered to be constant. In this case, volume is kept constant, which means volume at this point, volume 2, V2, is equal to volume at this point, which is V1. So this is considered to be the isochoric process. In a piston form, this volume is kept constant, but the process goes from this pressure to this pressure. There is a change in pressure value from P2 to P1, but the volume is constant. Due to that, we get the work done is equal to 0. So the energy Q value, which is applied to this system, is used not to change this. The position of this piston will not go from here to somewhere else, but it can be used to change the internal energy of the particle. The translational kinetic energy of those gases may be increased rotational or vibrational energy of the particles. Okay, the other one that we get is the adiabatic process. In an adiabatic process, the system does not change heat with its surrounding, that is Q is equal to 0. So the first law for an adiabatic process takes this form. The work will be equal to the change in internal energy of the system. So because Q value is 0, so you can take this an example. There is a pressure versus volume graph. So this is a thermodynamic path. This is state 1 and this is another state 2. So here we have P1, V1, T1. Here we have P2, V2 and T2. So when you do a work, that means, for example, if it goes from state 2 to state 1, from state 2 to state 1, when you push this in this direction, so it goes here, then in this case the process goes from state 2 to state 1, so there is an increase in pressure. The pressure at state 2 is P2, the pressure at state 1 is P1, so P1 is greater than P2, so there is an increase in pressure, but there is a decrease in volume because volume V1 is less than V2. So as you can see here in this diagram, so previous in the beginning state 2 we have this much pressure, so when you push this upward you'll get this volume, small volume value. Due to this there is an increase in pressure. So such type of system with Q kept constant, there is no change in Q value, the work done will be used to change the internal energy of the system, so that is called adiabatic process. Okay, so actually if you consider this one, if it is downward in this direction it is expansion, the other is compress. So there is adiabatic process. This is isothermal process at constant temperature. When it goes in this direction, it's considered to be the adiabatic process. Then the work done will be the area bounded by this line. Okay, the other one is isothermal process. It is a process which involves no change in temperature of the system. Isothermal process. So if the process occurs at constant temperature, then there is no change in the internal energy of the system. So first law for isothermal process take the following form, where change in internal energy is equal to the work plus Q value. So in isothermal process the temperature is constant. Due to this value becomes 0, so the heat supplied will be equal to minus of this one. For ideal process, that means if you have a gas, then the equation of state can be represented by PV is equal to nRT, so divided by V, so you get P is equal to nRT over T value. So work is equal to the integration of P dV, so P is equal to nRT over V. So when you remove out from the nRT is constant, N is constant, R is constant, T is constant because it's an isothermal process. So when you come out dV from the integration 1 over V, we get ln of V final minus ln of V initial, which is ln of V final over V initial. So you get the work using this formula. This is an example of an isothermal process constant. So this is the formula that you get in order to get the work P dV, where P is equal to PV is equal to nRT, therefore P is equal to nRT over V. So N is constant, R is constant, T is constant, so the work is equal to from V initial to V final dV over V. So when final result will be ln of V final V initial. So with this we can get the result easily. Okay, the other is isobaric process. In isobaric process, the expansion or compression occurs at constant pressure. Any work done by the system will result in an increase in volume. So the work done in the pressure volume graph is equal to the area under PV graph. For isobaric process, the work done is calculated as P change in V, because isobaric indicates at constant pressure. This P is constant, so P multiplied by V final minus V initial. So in this case we get 0, which is work plus Q value. So Q is equal to the heat supplied to the system is equal to minus value of W. So the first law of an isobaric process can be written simply: the change in internal energy is equal to Q plus the work. So Q, and the work is equal to minus times change in V minus, we consider this minus sign, so Q P V final, this one minus V initial, so it can be used for finding fun. So based on that, it's possible to solve this example. The example says 500 joule of heat are added to 2 moles of an ideal monatomic gas initially at temperature of 500 Kelvin, while a gas performs 7,500 joule of work. What is the final temperature of the gas? So you need to consider the change in internal energy is equal to Q plus the work done. We know that the heat supplied is 5,000 joule of heat added to this one. So the work done, which is while the gas performs this much amount of work. So what is the final temperature? So we need to subtract, and finally get 2,500. And the internal energy is equal to n heat capacity multiplied by change in T value. So we have got this 2,500, and then now we apply this change in U value, and finally you get nr change in T. Note here we are going to replace this heat capacity value, and it becomes over to nr change in T value. So n is known, which is 2 mole, multiplied by r is constant, which is 8.31, and finally the change in temperature is equal to it's around minus 100 Kelvin. So this will be the change in value. So T final minus 500 K, which is equal to minus this much, so the final is 400 K value. So the gas does more work than it takes in as heat, so it must use 2,500 joules of the internal energy. Okay, this is also another example. We have 2,000 joule of heat leaves the system. Remember, it leaves the system, and 2,500 joule of work is done on the system. So what is the change in internal energy of the system? This much is done on the system, this one leaves the system. So the internal energy Q plus this, so this one leaves the system, so we need to have a minus sign, but this one is added to the system, this work done on the system, not by the system. So finally the internal energy would be 1,000 joule. So if this one not leaving the system, if you add this much to the system, so we finally will get 3,000 plus 2,000, it will be 5,000. But in this case, it's this one leaves the system. This amount of heat leaves the system. That's why we put a minus sign. Okay, so the internal energy increases by 4,500 joule. 2,500 and 2,000, so there is 4,500. This is just the change. Okay, so this is the end of chapter 4. See you